Hello, my name is Marija Furdek, and I will present a talk on root cause analysis for autonomous optical networks, focusing on a physical layer security use case. I would like to extend my gratitude to the organizers and chairs for inviting me to present this talk, which is a collaboration between Chalmers University of Technology in Gothenburg, where I work, and Telecom Italia in Italy. As this is an invited talk, I would first like to give a bit of a broader background and introduction to the challenges tackled in this work and describe the experimental testbed settings which we have used to obtain all the results that I will show. I will focus on machine learning approaches for security diagnostics, in particular on their performance and challenges related to accuracy, runtime complexity, and interpretability. As we know, communication networks are targets of a multitude of different attacks, and this creates a lack of trust and security in cyberspace that in turn jeopardizes the digital evolution. So multiple bodies have emphasized the need to step up the global efforts to address an increase in cyber attacks and security breaches. Cybersecurity risks are seen as the number one threat to businesses as well, where they can incur financial, legal, reputational, and operational losses. The network infrastructure security ranks very high as extremely challenging factor. It is fundamental to have a reliable and secure network infrastructure in order to achieve privacy and protection. In optical networks, the situation is not an exception to the general trends. There's a multitude of breach incidents that are reported at a yearly base, but of course most of them go unreported. The factors that make optical network management complex are the fact that the fiber plant is deployed in unprotected environments, it proliferates, and it is extensively shared. The data rates that are carried by the fiber are unprecedentedly high, and the optical reach is extremely long. So all of this makes it difficult to track the status of the signals at each point in the network and at all times. Attacks that target the physical layer of optical networks are broadly divided into eavesdropping and service disruption categories. In eavesdropping, the aim of the attacker is to gain access to information in an illegitimate way. It can be done by abusing, for example, well-known monitoring techniques, which is shown in the illustration, where a temporary coupler is created by bending the fiber. The losses that are caused by these intrusions can be undetectably low. The protection from eavesdropping relies on encryption at different network layers. Service disruption attacks are aimed at disrupting or degrading the services. These techniques are very diverse. They differ in their persistency, overtness, confinement, and so on. And their consequences also depend on the way that the network is designed and the services are provisioned. Due to these challenges, in our work we focus on service disruption attacks. Some of the techniques that can be used to disrupt services are listed here. For example, critical components can be disabled by cutting the fibers or performing electromagnetic pulses. Harmful signals can be inserted into the network to cause jamming. The jamming can be in-band if there is overlap in the spectral domain, or out-of-band if there is sufficient difference between the jammed signal and the jamming signal. External polarization scrambling is an attack technique that doesn't require fiber intrusions. Instead, the fiber is squeezed and it changes the polarization state of the light. So this results in errors when the polarization modulation is faster than what the coherent receiver can recover from. In our work, we focus on these two techniques. The two techniques are tested in an experimental testbed by Telecom Italia. The testbed is a realistic setup that has 6 reconfigurable optical add-drop multiplexers, and it's equipped with off-the-shelf coherent receivers. We then subject this testbed to the attacks that is shown in the right purple blocks. The sine wave generator is used to drive the fiber squeezer to scramble polarization of the signal, and the continuous wave laser is used to insert jamming signals. So what does it look like in the spectral domain? In the baseline case, when none of the attacks are on, we have 2 channels under test that are depicted here with blue and red. And we have 4 loading channels to depict realistic loading conditions. When polarization scrambling is on, then we turn the sine wave generator on and we change the amplitude of the sine wave signal to achieve a lighter and a stronger attack intensity. When out-of-band jamming is performed, a jamming signal is injected in the link under attack. It is sufficiently distant from the channels under test, and we tune its power levels to again emulate a lighter and a stronger attack intensity. When in-band jamming attack is performed, the jamming signal overlaps with the channel under test, and again its power level is changed to emulate a lighter and a stronger attack intensity. In this way, we collect a rich data set where each of the described condition is observed over a 24-hour period, and each minute one sample is collected. One sample contains the features described in the table on the right, and an advantage of this scheme is that it doesn't rely on any monitoring data at intermediate nodes. Instead, it just collects the signal health information from the destination where it needs to be detected anyway. Here we are plotting some representative parameters across all 7 observed regimes: the optical signal-to-noise ratio, the received optical power, and the bit error rate before FEC. What we can observe from here is that there are no clearly identifiable thresholds or consistent trends in the data that could serve as an indicator of an attack, and we need artificial intelligence and automation of these tasks. When we apply machine learning for security monitoring, one of the first go-to techniques is supervised learning. It relies on a representative data set that is labeled by the experts and used to train the algorithm. In other words, we have a complete information about what should be learned. This allows us to obtain fine granular diagnostic information from supervised learning techniques that can report on the presence of an attack, its type, intensity, or even location if this is what we trained for. In our work, we applied an artificial neural network to the data set that we obtained from the testbed. And here we can see the confusion matrix that maps the percentage of true attacks on the vertical axis and the prediction of the algorithm on the horizontal axis. As we can see here, artificial neural network performs very well, with only a minor confusion between the intensity of the polarization scrambling attack. For more details about different supervised learning approaches, I would like to refer you to the paper below. However, in spite of the very good performance of the ANN, we need to be aware of several things. First of all, the security threat landscape is not final. Threats evolve and new ones emerge. And we need to take into account that it's not always possible to have a representative data set. And even if we did, labeling of the data can be infeasible or too costly. So as a result, complete information about what should be learned is not always available. To tackle these issues, unsupervised and semi-supervised learning techniques can help. One thing in common with these two techniques is that they don't require any prior knowledge of attacks. And as a consequence, on the downside, they can only report on the attack presence. They simply don't have sufficient information to do further categorization of attacks. Unsupervised learning doesn't use any labeled data. There is no clear mapping between the inputs and the outputs or the normal and abnormal conditions. So the algorithm learns to identify similarities among different inputs, to cluster the data, or to extract features. A technique that we used is density-based spatial clustering of applications with noise, or DB-scan, that works by clustering the monitoring samples and identifying anomalies as outliers. The performance of DB-scan is fine-tuned by changing the values of the two design parameters that define the distance between two samples to be considered neighbors and the number of samples within a cluster to be considered normal. In semi-supervised learning, a small amount of data is labeled. In our case, for example, the normal operating conditions are known, but the attacks aren't. So the algorithm is trained to detect outliers. We used one-class support vector machine, or OCSVM technique, that infers the properties of normal cases and distinguishes them from abnormal ones by confining the normal ones within a region as tightly as possible. Adoption of unsupervised and semi-supervised learning techniques comes with a certain set of challenges that is quite broad, but in our talk we only focus on 3 of them, related to accuracy, runtime complexity, and interpretability. When it comes to accuracy, our aim is to detect as many attacks as possible, in other words, to reduce false negatives, and at the same time minimize the likelihood of false alarms. Those are caused by false positives. So to illustrate the performance of different machine learning algorithms, we will use 3 representative techniques from each of the machine learning category, and we will plot their performance in terms of the obtained false positive and false negative rates. False positives mean that an attack-free sample will be categorized as attack, and false negative means that an attack sample will go undetected. Another metric that can be used is the F1 score that summarizes the performance of the machine learning algorithm as a single digit. Let's begin with the DB scan. Here we can see the different values that are obtained by the different parameter settings of the algorithm, and we are plotting the Pareto frontier here. There are other points that have been obtained, but they are worse than along this frontier. For example, the best F1 score that was achieved was 0.8. And if we were to prioritize false negative rates at the expense of a higher false positive rate, we can go a little bit further in the false negative rate. The performance of the OCSVM is a bit better. Ideally, we would like to have 0 false positives and 0 false negatives. This performance is a bit more scattered for the different parameter settings, and the best F1 score achieved was 0.96. The artificial neural network had 100% accuracy. To improve accuracy of the semi and unsupervised learning models, we proposed a window-based attack detection approach, where we define an observation window that contains delta samples, and we can also denote that upon the attack occurrence, all the samples are actually denoted with gamma. We then set a threshold on the number of positive samples required to raise an alarm. It's denoted by tau. Now, by tuning the values of gamma and tau, we can achieve different trade-offs between the time it takes for an alarm for an attack to be detected and the probability of false alarms. So, if tau is equal to 1, the detection will be faster, but the false alarm rate will be high. On the other end, if tau is large, then the detection will be correct but slower. So depending on the priorities of an operator, a good value of tau can be around 3 or 5, somewhere in this region, where we need to balance reconfiguration or recovery actions that are triggered by false alarms and the overhead it incurs with the time to detect an attack. More details are provided in the paper cited below. The second challenge that we tackle here is related to runtime complexity, where we would like to reduce the processing load by using the most relevant dataset features. As we noted before, the dataset provided by the coherent receivers can be quite extensive, and at the same time we would like to have the algorithm as lightweight as possible. The dimensionality reduction techniques are applied to this end. Traditionally, the pipeline looks like this. We have a certain data set that has a certain number of dimensions, or in our case, features or OPM parameters. Then this data set is transformed and normalized and fed to the semi-supervised or unsupervised learning models, which then report back on the detected anomalies. Alternatively, we can first apply dimensionality reduction techniques to the dataset before we process it with the models. There are different dimensionality reduction techniques that can be applied. In our case, we applied 3 of them. The first dimensionality reduction technique that we applied is principal component analysis, or PCA, that encodes as much variance as possible from the original dataset to the encoded dataset. The second technique is t-distributed stochastic neighbor embedding that tries to encode the distances between the samples in the original dataset into the encoded dataset. Finally, the autoencoder is an artificial neural network that contains a feature extraction layer. It has as objective to map the outputs to the inputs as close as possible. After the training, the encoder part of this structure can be used for dimensionality reduction. In order to understand how the dimensionality reduction techniques affect the performance of the OCSVM and the DB-scan, we combined each of them with the 3-dimensionality reduction techniques and compared it to the full dataset case, denoted with red. The different shades of each color represent the different number of features, which were varied from 1 to 7. If we take a look at OCSVM, we can see that it doesn't really benefit from dimensionality reduction. However, OCSVM requires an initial training and characterization of normal working conditions, which in reality might increase the complexity of establishing a new light path in the network. However, DB-scan obtains significant improvements, so in the next slide we are zooming into the performance of DB-scan. We isolate only the PCA and TSNE, which are the most promising dimensionality reduction methods. We can see that TSNE achieves much better performance at the expense of higher runtime, and this is expected for this method. In PCA, on the other hand, we obtain benefits in both metrics. It reduces the runtime and achieves much better performance compared to the full dataset case denoted in red. For more details, I would like to refer you to the paper cited below. The final challenge is related to interpretability, and this is the first time that we tackle this issue. The aim here is to provide insight into the nature of detected anomalies to the security specialists. Why do we even need interpretability? So let's take an illustrative example of tracking the values of two parameters over time, which vary. And at some point, the machine learning model will tell us that there's an attack. It has detected an anomaly. At this point, the security specialist doesn't know why this alarm was triggered, which parameter caused it to be triggered, and which are the contributions to the alarms of each of the parameters. So what we do is we propose a root cause analysis framework for security diagnostic purposes. Traditional flow of actions looks somewhat like this. First, performance data is retrieved. It is stored for future use. And then anomaly detection is performed by applying the machine learning models that we presented before and potentially coupling them with the window-based attack detection approach to improve their accuracy. The part that we proposed here is the root cause analysis, which takes a deeper dive into the trends observed in the data. And in the end, it also provides a visualization tool in terms of the anomaly vector. So how does this block work? It works by analyzing the distances between the samples that are within different clusters. In this case, we only show the attack. This is shown in red, the attack cluster and the closest normal cluster to it. So for each feature, we calculate the average value over the samples that are contained in the attack cluster and the normal cluster that is the closest to it. We then express these values in terms of the anomaly vector, which is shown here with red, that indicates that feature number 2 deviates the strongest from the normal conditions. When we apply this technique to the experimental data set that we have at our disposal, we can identify some interesting insights into the trends. First of all, in the jamming attacks, both in-band and out-of-band jamming, the OSNR and the Q factor are the most affected by jamming. This is something that we can expect. In polarization scrambling attack, the trends look significantly different. Aside from OSNR and Q factor, chromatic dispersion and differential group delay are also affected. Some of the trends observed for these attacks are different from what one could expect. This means that the anomaly vector tool goes beyond simple OPM time series visualization, and it eases the physical interpretation of the anomaly. To conclude, we can point out that optical network security management automation requires interpretable machine learning techniques that have high accuracy and low complexity. To address the issue of interpretability, we proposed a root cause analysis framework for security breaches, and the anomaly vector tool shows that some of the OPM parameters that are typically disregarded can serve as attack indicators. The root cause analysis still needs further studies, where it can be complemented with other data sources and newly emerging root cause analysis techniques. I would like to point out that the implementation of the approaches that I presented here can be found in the GitHub channel of Carlos Natalino, my co-author. And for all questions, please feel free to get in touch with us. Thank you for your attention.